Hey everyone, and welcome to this explainer. I want you to think for a second about the very last thing you tossed in the garbage today. Maybe it was a paper coffee cup, a broken charging cable, or just some leftover food. What if I told you that absolutely everything we've been taught about that trash is fundamentally wrong? Today we're exploring a radical paradigm shift in how we view the physical world around us, diving into the core foundations you'd expect from Introduction to Circular Economy Book 1, Session 3. We're going to be specifically focusing on resource recovery and getting energy from waste.
Okay, let's dive into this. 1. Rethinking the trash can. 2. Powering up with waste. 3. Mining our modern trash. 4. The limits of circularity. And 5. Making the system work.
Section 1. Rethinking the trash can, from endpoint to starting point. For generations, we've essentially operated on a linear economy, a take-make-dispose model. We just assumed resources were endlessly abundant, and once we were done with a product, it had zero value. Well, the circular economy completely flips this on its head. It treats waste simply as a resource in the wrong place. Those discarded items in your bin, they are garbage. They're incredibly valuable physical, chemical, and energy resources just sitting in the wrong bin, waiting to be recovered.
Now, what's really interesting about this slide is the concept of embodied energy. Every single product contains a massive hidden investment of energy. Think about a standard glass bottle. Energy was used to extract the raw sand. Fuel was burned to transport it. Massive heat was used in the manufacturing process, plus all the energy for packaging and distribution. When you toss that bottle into a landfill without recovering it, all of that invested energy is instantly, permanently lost. But by reusing or recycling it, we preserve that hidden energy.
So to manage these resources, we use a hierarchy, kind of like a funnel. We always want to start at the top by reducing and reusing. But step 4, recover, is where waste to energy, or WET, comes in. Now, it's absolutely crucial to understand that converting waste to energy is not our first choice. Recycling is much more energy efficient. But for non-recyclable materials, recovering that stored chemical energy is a massive, highly sustainable upgrade from simply dumping it in step 5, the landfill.
Section 2. Powering up with waste, the energy engine.
This brings us to biomass. By definition, biomass is organic material. We're talking things like agricultural residues, wood chips, and food waste. But if you really think about it circularly, biomass is actually an incredible, continuously replenished solar battery. See, plants absorb solar energy through photosynthesis, and that energy gets safely stored in their chemical bonds. When we manage this sustainably, we can unlock that stored power to literally run our world.
So, how do we actually get that energy out? Well, we use some brilliant thermochemical and biochemical methods. For dry waste, like wood, we can use combustion for direct heat or gasification to create a really versatile syngas. Notice pyrolysis on the list there? That's heating woody biomass in the total absence of oxygen. This creates bio-oil and something called biochar, which is incredibly prized because it can sequester carbon in the soil for centuries. For wet waste, like food scraps or corn, we switch to biological methods like anaerobic digestion and fermentation.
And this brilliantly illustrates one of the most effective biological methods, anaerobic digestion. We take wet organic waste, put it into a sealed oxygen-free digester tank, and just let bacteria go to work. The bacteria break it down and produce two amazing things. First, biogas, which is mostly methane, that goes straight up to power grids and generate heat. Second, the leftover material becomes a nutrient-rich digestate, which goes right back into the soil as an organic biofertilizer. It's basically a perfect closed resource loop.
Now, it's super easy to mix up the terminology here, so let's clarify the difference between biogas and biofuels. Biogas, which we just looked at, is a gas produced biologically. It's often highly decentralized and mainly used to generate electricity and heat locally. Biofuels, on the other hand, are liquid fuels like ethanol and biodiesel. These require much more industrialized processes like fermentation or complex chemical reactions, and their primary job is to directly replace petroleum in our cars and transportation sector.
Section 3. Mining our modern trash, logistics, and extremes. Shifting our focus from organic waste over to industrial logistics, resource recovery isn't just a matter of taking out the trash. It's a highly sophisticated logistical loop. It starts with collection, where purity is absolutely key. The cleaner the waste, the easier the recovery. Next is sorting, which relies on high-tech optical sensors and massive magnets to segregate the materials out. Then comes processing, like shredding plastics or crushing glass into what's called cullet. Finally, utilization. This whole system only works if there's a viable end market, returning these materials right back into manufacturing or agriculture.
But what about waste that's just too dangerous to recycle? Well, we hit it with 5,000 degrees Celsius. That is nearly as hot as the surface of the sun. It's an awe-inspiring process called plasma gasification, and we use this for hazardous and medical waste. The plasma torch literally breaks down dangerous materials into their basic elemental atoms. What you get left with is a usable syngas and a completely safe, inert, glass-like slag. No toxic footprint left behind. Then we have electronic waste, or e-waste, which is the fastest-growing waste stream on the entire planet, and it presents a really fascinating paradox. On one hand, it's a severe toxic hazard if things like lead and mercury leach into the soil. On the other hand, it's a highly concentrated urban mine. Think about it. A discarded smartphone or laptop contains gold, silver, palladium, and rare earth elements in concentrations that vastly dwarf the natural ores we dig out of the ground. Mining our cities is literally becoming more lucrative than mining the earth.
We also have to surgically manage other highly specialized waste streams. Construction waste is huge just by weight, so we're now crushing concrete into recycled aggregates and literally designing buildings like Legos, a concept called design for deconstruction, so they can be taken apart later, not demolished. With fast fashion, textile waste is a total chemical nightmare because of blended fibers like polycotton, which require complex molecular separation. And as for electric vehicles, dead EV batteries actually get a second life as home solar storage, before finally being shredded into highly valuable black mass to recover lithium and cobalt for brand new batteries.
Section 4. The limits of circularity, the reality check.
So let's ask a fundamental question here. If all these recovery methods are really so fantastic, is 100% circularity physically possible? Like, can we just recycle the exact same materials over and over again forever, with absolutely zero waste?
So the crucial point is, no, we cannot. And the reason is literally a law of physics. The second law of thermodynamics states that every single energy conversion process results in energy loss, usually as low-grade heat. It means that the quality and usefulness of energy degrade over time. Because of this unbending rule of the universe, perfect 100% circularity is a physical impossibility.
These thermodynamic limits translate into some pretty harsh realities on the ground. We're always going to face incomplete material recovery just due to standard contamination. The recycling process itself requires energy, and part of that is always lost. Materials also degrade. Paper fibers get shorter, plastics weaken, which leads to what we call downcycling. Even the most perfectly designed closed-loop system in the world will always require some external energy input just to keep running. So our goal isn't absolute, flawless circularity. Our goal is maximum achievable efficiency within the limits of physics.
Section 5. Making the system work. The human element.
Look, just knowing the physics and having the technology isn't enough. To truly transition away from a take, make, dispose world, we need a tripartite foundation to synchronize all of our efforts. We need policy frameworks to set the rules and mandate the change. We need economic frameworks to ensure that recovering resources is actually financially viable compared to just digging up cheap virgin oil or metal. And we desperately need social frameworks to protect the humans navigating this massive global transition.
Let's look at two specific examples of how these frameworks operate. In policy, we have Extended Producer Responsibility, or EPR. This shifts the financial burden of waste right back onto the producer, forcing them to design for environment so their products are actually easy to recycle from day one. Over in economics, we rely on things like tipping fees. This is the fee a waste-to-energy plant charges just to accept trash. When you combine that tipping fee with the money made from selling electricity and recovered metals, you create a triple revenue stream that makes these extremely expensive recovery facilities financially viable.
Ultimately, it all comes back to our core thesis for this explainer. Waste is not an endpoint, it's a starting point. And as we build this new system, social frameworks are vital. We have to ensure a just transition. That means retraining traditional landfill operators for high-tech recycling jobs and formalizing the roles of informal waste pickers globally. We need to ensure they have safety gear and stable wages, rather than just displacing them with automated machines.
We've covered a massive amount of ground in this explainer today, from the embodied energy in a simple glass bottle to the 5,000-degree plasma torches mining our electronic waste. So I want to leave you with this final, provocative thought. If your trash is actually a treasure holding embedded energy and rare elements, what are you throwing away today that could power tomorrow? Thank you so much for joining me for this explainer, and I really hope you never look at your garbage bin the same way again.